AP Calculus AB, we are looking at optimization problems. This is an introduction. So the first thing we would want to tackle is, what is optimization? Optimization is the process of making something the best it can be given constraints. It involves maximizing or minimizing a certain value or quantity. Finding maxima or minima, both of those require derivatives. So we're going to be using derivatives when we're finding optimization of things. The general approach to solving optimization problems. 1, write an equation for the quantity you want to optimize. Often on these problems, they won't give you an equation. You have to form the equation on your own. 2, use whatever constraints that they've given you to find another relationship between the variables. That likely means you're going to have to come up with a second equation. 3, rewrite the main equation in one variable, the equation that you want to optimize. 4, identify the critical values by solving f prime equal to 0, and then use one of the methods below to determine the optimized value. Either use the candidates test, find the derivative, use the first derivative sign diagram, or use the second derivative test. And then lastly, interpret the answer in context. Let's just take a gander at an example called Down by the River. A man lives in a white van down by the river. While spelunking, he finds 1,000 feet of pristine fence. 1,000 feet of pristine fence, this is a constraint. He decides to build a rectangular enclosure along the river to mark his territory. If the side along the river needs no fence, what is the largest enclosure that could be made? The fact that it's asking for the largest enclosure, that's an optimization problem. Largest meaning the most area. That's implied but not said. So here is a picture. We got this blue part here is the river, and then we have this rectangular enclosure. There's no fence needed by the river. Calling these two sides width and this side length, you could have those mixed around, it really wouldn't matter. So step 1, according to this up above, write an equation for the quantity you want to optimize. Well, we want to optimize the area of this figure. So our equation is area is length times width. 2, use the constraints to find another relationship between the variables. Well, we have 1,000 feet of fence. So if we add this side and this side together and this side, that should be 1,000. So our constraint, 1,000 feet of fence, should be equal to 2 times the width plus the length. If you get one of the variables by itself, we will find that L is equal to 1,000 minus 2W. Step 3, rewrite the equation in one variable. The equation is the main equation here, which is area, what we're trying to find the largest area of. If you replace the L here with 1,000 minus 2W, now it's in one variable. If you distribute the W, we got this in a simplest form that the area is 1,000 times the width minus 2 times the width squared. Step 4, identify critical values by taking the derivative and set it equal to 0. So if we take the derivative of A of W and we set it equal to 0, we will find that the width of 250 is a critical value. We then want to take that critical value and determine, is this a maximum? So we're going to use the candidates test. Or we could use the first derivative sign diagram or the second derivative test. We're going to use the candidates test for this one. So what would my candidates be? The candidates are any critical values. So there's 1, 250, and the endpoints of the domain. So if we have 1,000 feet of fence for this width, the minimum the width could be is 0. And that means you just have 1,000 feet of fence right up against the river. That doesn't make sense, but that's something that you could do. We could maximize this width so that we had 500 feet on each side, and then they were squished up together with no area in between. And that's not what I wrote here, but I wish that I would have. Let me change this to 500. So if you use your equation for area and you put 0 into this, you're going to find that the area is 0. If you put 250 into this, you're going to find the area is 125,000. If you put 500 into this, you're going to find that the area is 0 once again. That gives us the absolute maximum of 125,000. That's the biggest number. And then the last step, identify the answer in context. The largest enclosure that can be made is 125,000 square feet, because the question was, what's the largest enclosure that could be made? So that's an introduction to optimization. It's the end of this video. There will be another video that follows this with some specific examples that we can look through, and we'll go through those from beginning to end.